Alright, the question says consider the following integral I subscript n alpha or alpha greater than 1 and positive n. I n alpha equals 1 over n to n f of alpha x minus fx over x dx. Assume that a real valued function of x is continuous and differentiable for positive x and its derivative is continuous and limit x approaches infinity fx is 0. Then answer the following questions. First part is define j n alpha as derivative of I with respect to alpha and show that it equals to this. They're saying that j n alpha is derivative of this f of alpha x minus fx over x dx. Okay, and I can write this as 1 over n to n. If I want to slip this derivative inside, I'll have to make it make it as a partial derivative because f is a multivariable function in both alpha and x. So that becomes a partial derivative of the same thing inside and dx as it is. Okay, so the numerator becomes f dash at alpha x times derivative of alpha x, so that becomes x because alpha is the parameter we're differentiating with, and the second term is a constant, so that's 0, and denominator relatives. So this and this they cancel out, and we get integral from 1 over n to n f dash alpha x dx, which is simply 1 over alpha f of alpha x n to 1 over n. So we get 1 over alpha f of alpha n minus f of alpha over n. And this is what they asked us to show. So we've done that. Now in the second part, they're saying define I alpha as limit n approaches infinity I subscript n alpha and show that limit n approaches infinity j subscript n beta exists and it inversely converges, and I have to show that I of alpha and this integral, they are the same. Okay, I'll start with g and beta first. Limit n approaches infinity j and beta, that is equal to 1 over beta limit n approaches infinity f of beta n minus f of beta over n. So this approaches f of infinity and this approaches f of 0. So this becomes f of infinity minus f of 0. So I get f of 0 over beta. Alright, this is our j and beta simplified. Okay, now they're saying limit from 1 to alpha for uh, this term, which is equal to this, minus f of 0 over beta d beta. That term is equal to 1 to alpha. F of 0 is constant, so that comes out. And we get this, which is very easy to find. That's ln of upper limit over lower limit, which is 1, so ln alpha. And they're setting it equal to I alpha. But what is I alpha? I alpha, that's limit n approaches infinity of I n alpha. So that's simply 0 to infinity f of alpha x minus fx over x dx. All right. So I'll go and do some manipulations here to simplify that integral. I'll write the numerator as f of x, y, and the limits for y are y equals alpha and 1, x as it is, dx as it is. And then I can further simplify that as 0 to infinity, 1 over x, 1 to alpha, derivative of f with respect to y, dy dx. So this term, this whole term, that's the same as numerator, so this is a valid substitution. Okay, and now I'll describe some fx in the form of some gx and take partial derivatives with respect to y on both sides. So I'll get del over del y of f, that's equal to del over del y of g. So f dash xy, partial derivative of this with respect to y, that's only x, and this is as it is. And if I take derivatives with respect to x, then I get this f dash xy times y equals del over del x. Okay, and from these two I can write that f dash at xy, that is equal to 1 over x del g over del y, which is equal to 1 over y del g over del x. This will come in handy. I'll mark that. Okay, but how am I going to use this? I'll first, for this first starters, I'll substitute f of xy as g. So that becomes 0 to infinity 1 over x, 1 to alpha, del g over del y, dy, dx. Alright, alright. And now this becomes 1 to alpha 1 over x, del g over del y, dy, dx. And now this I can substitute using this. So that becomes 0 to infinity 1 to alpha 1 over y del g over del x dy dx. And now if I switch the order of integration, we get 1 to alpha 0 to infinity 1 over y del g over del x dx dy. Now this is an integral with respect to x, so 1 over y is a constant. So that comes out 1 over y 0 to infinity del g over del x dx dy. So this simply becomes g at infinity minus g at infinity comma some y minus g at 0. Alright, and now g at infinity comma y, that becomes f of infinity times y, that's f of infinity. And g at 0 comma y, that becomes f at 0 times some other y, but that's again f of 0. So the integral, that becomes 1 to alpha 1 over y f at infinity minus f at 0 dy. And this term in f, that is a constant, so that comes out of the integral. And I'll again get this familiar integral, which results to ln of upper limit over lower limit, which is 1, so that's f of alpha. And I get f at infinity minus f at 0. And again f at infinity, they have given that is equal to 0, so this again becomes f0 ln alpha. So we got this integral I alpha, that's equal to the limit we were finding earlier for limit n approaches infinity a and beta, and that is equal to this. So we have proved this. Obtain I of alpha, that we already did, so this is also done. Now they're asking us to calculate this following integral. Okay, so that is of the form 0 to infinity e of minus px cosine of px minus e of minus qx cosine of qx whole divided by x dx. Okay, so if there's a function fx of the form e to the power minus x cos x, then this term is f of px and this term is f of qx. So that integral is just 0 to infinity f of px minus f of qx, oops, f of qx over x dx, which we just calculated earlier. It's of the form f at infinity minus f at 0 times ln of one parameter over other. Okay, so this is what we get. We just proved it earlier. And since e raised to the power minus x cos x, that is a continuous and differentiable function, f at infinity, that's limit at infinity for fx. So minus x cos x. So e to the power minus x, that goes to 0 and this oscillates. So I'll get 0. And for f of 0, limit x approaches 0 of x, limit x approaches 0, e minus x cos x. This goes to 1, this goes to 1, so this is also 1. So the final result is f of infinity, that's 0, minus f of 0, that's 1, times ln of p over q. And using laws of logarithms, that becomes ln of q over p. And that is the final answer. So part 4 is done.